So let's begin a discussion on random variables. A variable x is called a random variable if x assumes real values corresponding to each value that x takes there exists an associated probability. Number 3, the sum or integral of all probabilities is unity. So these three conditions must be satisfied by any variable to be called a random variable. Now, according as the values that x takes are discrete or continuous, random variables get defined as discrete random variables or continuous random variables. So we will just write as a note, if x assumes discrete values it is called a discrete random variable. If x assumes continuous values it is called a continuous random variable. Random variables are pretty common in many of the worldly aspects. You will find them in communication engineering, you will find them in day-to-day life, you will find them in the stock markets, everywhere. But depending upon the measurements that you make on x, we call it as discrete or continuous. Now, what are the concepts which go along with random variables? This is what we'll have to discuss. So, before we take up the concepts, I would just like to tell you that some of the very ordinary examples that we mention are with respect to dice and coins or playing cards or things like that, so that the concepts are easily understood. But when it comes to engineering applications, we need to connect these concepts in terms of the situations that arise in engineering. So let's get into the concepts of random variables. Let me now give you two examples, one for a discrete random variable and one for a continuous random variable. Again, we'll make these examples extremely simple so that we can launch into the bigger problems. Suppose we consider tossing of a pair of coins. So the sample space will consist of both heads, a head and a tail in two combinations, and both tails. So if you can now prepare a probability distribution for this random variable, we will have to first define what is a random variable. So this x has to be defined. Suppose we say x stands for the number of heads that occur. Unless you define the random variable, the distribution is not ready. So if you say x stands for the number of heads that occur, you can actually see this is one case where no heads are there, so x can take a value 0. Here you can find that there is one head, and then here we have got two heads. So these are the possible values that x can take in this problem. Now let us write the probabilities. When x is equal to 0, that means this is the case, it occurs once in 4 times. So 1 by 4 is a probability. When head is equal to 1, there are two possibilities, so it is 2 by 4, which is of course 1 by 2. And then when both the heads arise, it's only one case. So if you actually add all these things, you get a perfect one, which satisfies one of the axioms for a random variable. Alright. So you must have a sample space, provided it's a discrete distribution, and then you must have a definition for the random variable before you can fix the probabilities. This is an example of a discrete random variable. Now, x is called continuous if it has a density function. We'll come to the density function very soon, but broadly speaking, density function is a function which will assign probabilities to the random variable in the continuous case. So the density function is generally denoted by f of x. So as an example, suppose we take f of x is equal to 1 by b minus a less than x less than b, and 0 elsewhere. This can be a probability density provided certain properties are satisfied. One of the properties is, this probability definition should be valid for real values of x, assuming that a and b are real. So let us see this. And then the next important thing is the integral of this in this interval should be equal to 1. I think that anybody can verify, because when you integrate this function from a to b, you will get b minus a by b minus a, which is equal to 1. Therefore, it's a valid density. So it is very simple to understand that if x can take discrete values, you get an associated discrete probability distribution for the random variable x. Otherwise, you'll get a continuous case. And continuous random variables occur, wherever you are measuring a continuous signal over a small time window, whereas discrete is whenever there is breaks in the measurements. So let's actually get into the concepts now of random variables. What we can do with random variables, whether discrete or continuous, the concepts are very similar. The only difference is, in the case of discrete, summations are used for measurements or calculations, and in the case of the continuous case, summations are replaced by integrals. So let's get into the concepts. Now let's get into the concepts of random variables. In statistics, much before random variables, you have data, and then we are generally interested in two important issues. In fact, many more are there, but at the base level, there are two issues. Whenever you have got a data set, the first thing is to identify where the center of the data set is. And one of the centers that generally are used in statistics is the arithmetic mean. Of course, other centers like median, mode also exist, but in terms of reliability and simplicity of calculation, the arithmetic mean is preferred. So arithmetic mean is one of the very important statistical measurements that we make about data. The second thing is a measure of spread, and for that the variance is used, or its square root, the standard deviation, is used. Same thing when it comes to random variables, we are generally concerned about the mean of the random variable and the variance or standard deviation of the random variable. So borrowing the concepts from statistics, we extend them to random variables also. So in order to do this, we first require the concept of expectation. Expectation or mathematical expectation. So what's the definition? If x is a random variable, expectation of x is given by a summation or an integral depending upon discrete or continuous, summation xi into pi, I is equal to 1 to n, then xi or simply x into f of x dx, theoretically from minus infinity to plus infinity. Of course, depending upon the definition of the random variable, the limits can vary. So the expectation is given by either this formula or that formula, and you can actually see it is matching with the definition of arithmetic mean in the case of basic statistics. Now, how can we use this thing? So, expectation of x determines the mean of the random variable. So this has to be remembered. Another very important thing is the expectation of x minus mean. Suppose you call the mean as mu, x minus mu whole squared, and this determines the variance of x. Okay? If you simplify this formula, you can also call it expectation of x squared minus the square of the mean. So you can either use this or you can use this, and the square root of this is called the standard deviation. So therefore, we can make a small summary. Mean is expectation of x, variance is equal to expectation of x minus mean whole squared, standard deviation is the square root of expectation of x minus mu whole square. So the advantage or the requirement of doing calculations about mean and standard deviation is to basically locate the center and the spread of the distribution. One of the important questions or differences you must understand about variance and standard deviation is the units of standard deviation will be the same as the units of the mean. So therefore, many of us would like to work with the standard deviation. Variance is easy to compute because it does not have the square root symbol, but in practice we have to take the square root immediately to get the standard deviation. So I'm now going to show you one or two small examples of how to compute the mean or the standard deviation of random variables, but first we must understand whether it's discrete or continuous. Then there is a very important result called the Chebyshev's theorem, or it is also called the Chebyshev's inequality. This is with respect to the random variable x. Suppose for convenience we call this the density function of the random variable, where the mean is here. From the mean you measure k standard deviations on the right and k standard deviations on the left. So we should call this mean plus k standard deviation. We should call this location mean minus k times the standard deviation. Suppose you want to determine how much this area will be. If you want to determine how much that area will be, you can put it mathematically as probability mod x minus mu less than k sigma, and Chebyshev's theorem says this is at least 1 minus 1 by k squared. This is the Chebyshev's theorem. And if you look at the tail portions, probability mod x minus mu greater than or equal to k sigma will be less than 1 by k squared. This is a very important theorem by which certain general observations can be made about the a random variable. And you will see that one of the distributions that is generally discussed is a normal distribution, which comes under the continuous random variable case. But Chebyshev's theorem is a general theorem. The only difficulty about Chebyshev's theorem is it tells us within what limits we can expect the answer to lie. It does not exactly tell how much it is. And this is true for any random variable, even if you don't know its density function. If you know the density function, you can exactly calculate this LHS. But what Chebyshev's theorem tells us is, even if you don't know what distribution X follows, this is always true or this is always true. Okay. So we'll now get into the problems on random variables.